Well, hello, good evening, everybody. Not everyone gets the Pro Vice Chancellor of Research to warm up their audience, do they? So thanks very much, Sheldon. Thank you very much for coming. I appreciate that many of you have travelled some distance, so I'm very grateful for that. I had a look at the internet to see what inaugural lectures were really all about. And one prof from Bristol said that he saw it as an opportunity to celebrate the work of the team, the work of the research team. And I thought, what's that? A chance to blow my own trumpet? I'll definitely go for that. Did you want any more? Let me first of all introduce the team, because I do feel I was very lucky in what I'm about to talk about. I found myself really at the centre of a network, and I would say the most important partner in all this for me was, without a doubt, Dr. Dominic Egbeer. So are you here tonight, Dom? Dom. And he's kind of been our 3D printer man, and our man that keeps us abreast of developments in that area. And Dom's been central. Other central people have been the most excellent firm called Renishaw. Renishaw are a British firm for us to be truly proud of, with 14 Queen's Awards to industry. And they've been very generous. They let me print things out and try things out with their machines that cost £1 million plus, sort of thing. So I'm very grateful for that tie-up as well. They've been central. And Brian Austin's here, I think, and I'm not sure if did Dave get here? Oh, okay. Not many people go abroad to miss my lectures. That's quite impressive. And Dr. Quentin Jones, he's our sort of clinical wing. So thanks very much. So that roughly is the network. And I know that sounds like a lot of name dropping, but it is quite important, really. So tonight, the sections of my talk tonight basically fall into two. So roughly, to use the jargon, these are the lesson objectives. So first of all, I'm going to talk a little bit about innovation, which is part of my title. Then I'm going to talk a little bit about the traditional processes that are used in dental technology, so that people will be aware of the digital processes that we developed that are or potentially can replace some of these traditional processes. So some of you here are sort of specialists in the area. Obviously, you will know about digital processes brilliantly. I just need your indulgence because there are a lot of people here who are non-specialists, and for the rest of the lecture, to make sense, I need to go over those processes. Okay, let's have a look then. So my first point is about innovation. Now, I've never been taught this subject, and the first thing that strikes me about innovation, if you're innovative, you probably don't need to tell people that you're innovative, like my title does. But I didn't put that forward. It's something that the professorial committee suggested, and I'm very grateful to them. And I think they put their finger on something, because I really do get a kick out of new knowledge. But this is what the great historian and philosopher of science, a chap called Thomas Kuhn, who was working mainly in the sort of 70s and 80s, said about innovation in science. Most advances arise from either fresh young minds to a discipline or from those who've moved into new disciplines. Well, I think you can clearly see that in what I'm about to say and what I've already said about the link we've had between our section and the PDR. So that was Thomas Kuhn. One of the interviewers in the BBC, a chap called Melvyn Bragg, has probably interviewed more of our top scientists than anyone else. And he waxes lyrical about the unintended consequences of science, the unintended consequences of doing something. And this features large in the research I'm about to talk about. Will you just listen to what Melvyn Bragg says about unintended consequences? This isn't he's not doing my talk for me. This is only going to take about 2 minutes.
Hello, I'm interested in mathematics, wrote the Cambridge mathematician G.H. Hardy, only as a creative art. Hardy revered pure maths and scorned its application to the real world. In Great Mathematics, he wrote in the same book, published in 1941, there is a very high degree of unexpectedness. Yet what Hardy himself never expected was that in the decades since he wrote those words, pure mathematics would yield such an array of unintended consequences, not least through the wartime work of his Cambridge colleague Alan Turing, whose experiments with prime numbers led first to his crucial role in beating Hitler's codes and then to the birth of the computer.
So there's an example of someone who's a great mathematician, didn't want his maths to be used by anybody, and blow me, they were used by Alan Turing in cracking the Enigma code and are central to many processes on the internet. Unintended consequences. And the third thing I want to say about innovation involves eccentricity. This is another BBC interviewer interviewing several innovators who have got multi-million-pound businesses, one of which, incidentally, is creating artificial snow. Again, this is the last sound clip I'm playing, so just bear with me, please.
Here's my question. In light of that phrase you see stuck up in some offices, you don't have to be mad to work here, but it helps. Is that slightly true of the inventor's career, do you think? Delusion? You have to be a bit delusional to keep yourself going at times?
I think vivid imagination.
Yeah, absolutely, yeah. But and you have to think laterally. I can never go anywhere without seeing a way to improve it. Even as I sit here in the studio, I can think of a better way to lay out the furniture in here. So I'm always problem solving. And it's that fun of problem solving that makes you a great kind of inventor in many ways. And it's almost genetic. It just goes on all the time. I even solve problems in my dreams.
Okay, let's turn our attention to teeth then. We've finished with innovation for now. And I wonder if you've ever thought how important teeth are. While you're sort of imbibing that slide, I'll just read. Somebody sent me a book on teeth. I don't know why they thought I'd be interested, but this also shows how important teeth are. A survey of nearly 5,500 American singles by the online dating service Match.com found teeth to be the number one attribute both men and women use to judge potential partners. Yes, teeth matter. So I'd like to recommend to everybody that you do hang on to your teeth. But if you're unable to hang on to your teeth, there are some very real possibilities. Sorry, Phil, oh no, it hasn't. I thought it had gone blank. Now, say, for example, this was somebody's oral cavity. There are spaces here. And one way of restoring something like that is to make something like that. This is a metallic framework, and it kind of clips in place. And you see very little of it from the front. But that's something that's made specifically for an individual. And the reason I'm showing it is that we managed, one of the first things we did was to digitize that process. That was something within this field called prosthodontics. So we'll talk about that later. And we've also started to digitize some processes in the other field of orthodontics, which is kind of moving teeth around that are in the wrong position. Now, you can't do anything very much without something called an impression. And the basic idea of an impression is that you get some squidgy material, you put it in a container, you put it around somebody's oral tissues, you wait for it to set to a sort of rubbery consistency. And when it's set, that's called an impression. And then you can just flow gypsum into there or plaster into there, let it set, tidy it up, and you get a nice dental cast or model. The process isn't usually as messy as I was showing you there with that patient, but it's not the most comfortable process in the world. So these are the traditional processes. Once you've got a dental model, you can then, there might be, for example, somebody might have a tooth that's just got a stump on it, such as here. That crown's been cut away by the dentist. It's been left in the mouth. And you can make a crown or a bridge, and they're cemented in. They're cemented over it. And the way you make that crown is you build it up in wax and carve it. That's the thing you can see there in red. And then what you do is you have to, sorry, that's the thing you can see there in red. Then you have to attach a channel to that red wax, that's the blue wax. You surround it with a plaster-like material, let that set, put it in a furnace, the furnace burns all the wax out, and then you can pour molten metal into that mold, and you get something that you can see on the right there. This is known as the lost wax process and was used in the time of the ancient Greeks even for casting statues and things like that. So what has been happening in that field of crown and bridge for 20, maybe 30 years is that there is a digital process. And the idea is that there is a scanner, a three-dimensional scanner, which can scan the inside of somebody's mouth. So just as you saw that dental cast there with a stump, this is a 3D model with a stump. And then instead of building it up in wax, you can see on the left there, it's built up on the computer screen. So the shape of the crown going over it is built up there. That's a 3D computer model on the left. And then the computer controls a milling machine, which you can see on the right. And this milling machine cuts the shape you can see in the computer out of a solid block. So that's been going on for quite some time. And it has brought certain advantages, things like accuracy and fit. Unfortunately, it probably hasn't brought the cost down yet. But as these processes get more and more automated, I think we could expect the costs to start falling. Although, of course, dentists will probably try and prevent that happening. But that milling will really only do for fairly uncomplicated shapes. And fortunately, it's only one way of manufacturing something. It's probably not suitable for complex shapes. So again, if I can just remind you of this thing with it, with a very complicated, the metal framework is really far more complicated, isn't it, than that crown that you saw earlier. Now, it would be almost impossible to mill that, we think, with current technology, because the cutting materials will actually flex the alloy, the block of alloy that it's being cut out of. So huge difficulties for that. And this is where we started, really, because one of the first machines to build something layer by layer, 3D printer, arrived in this university, and we had a model already made of a sort of a framework. It wasn't like this, but it was ready to be linked to this machine that had just arrived, and we actually managed to build one of these complicated shapes. How do you do that? How do you do that? Well, first of all, you need a 3D scan. So you can see, that's the sort of complicated shape I was talking about. Okay, it's very difficult to mill that. How do you build it? Well, you scan a model. That's that small white model, more or less just below the center. And there's the 3D scan of it in the computer coming up. And once you've got the 3D scan in the computer, you can start to build up the sections of that complicated framework onto it. And this is where DOM really began, because in the early days there wasn't any dedicated dental technology software to do that. So we were using a package that was really put together for things like toy manufacturers and things like that. So that's where Dom applied his skills. And non-dental software. And eventually an image like this could be built and formed. It was a bit of a struggle because, as I said, there were no dedicated software to do it. And once you've got that image in the computer, the computer will layer it, slice it, as it were. So the whole form is built up, slice by slice, or layer by layer. So just to give you an example of this, say, for example, you had a magic bath of liquid that if a laser beam passed over it, it would polymerize, it would solidify. The computer controls the laser beam, it flicks over one slice of the image, solidifies it, then it moves down and does the same for the next image, and so on. So the first layer is hardened by the laser beam, following a pattern that the slice of the image produces, and then you build it up. Okay, so this is one of the machines in the PDR. The liquid is in that big bath on the left there. If you can just see to the right a small pattern, which is a pattern of one slice of something being built up, and the laser beam sort of follows that pattern in that slice and hardens it layer by layer. And here's one of our first patterns emerging. This was in plastic, actually. But there are quite a few labs that are building these frameworks like this. They're not producing it in plastic. They tend to produce it in wax, first of all. But this is where we started, and those are my hands. They're famous hands now. And you can adjust the plastic a bit. And then in the same way as I was describing how a crown was formed, you put channels down to that plastic pattern, down to that plastic pattern, surround it with a plaster-like material, put it in a furnace, it all burns out, even the plastic burns out. And these channels are sticking out of the mould, of course, and then you pour molten metal through the channels and it fills up that shape there. And actually I think that was the first one we ever built in that manner. But this phase didn't last long, because quite quickly machines which would actually build directly in metal came into being. And the way they do this is it's still built layer by layer, but it uses powdered alloy, and a powerful laser welds the powder together layer by layer. So it does one layer, then it welds the next layer, and so on. This is our first RP, removable partial denture framework, as they're called, emerging on the left with supports that are needed. And on the right, that was the same framework you can see on the left. It's filed up and polished. And we popped it in the patient's mouth. And we were very pleased with the results. And we actually wrote it up. Now, I know you can't read this, and you should never, if you're presenting, you should never put a slide up like that your audience can't read. But I was so proud of this paper, which was the first one to describe this technique. And this was in the Journal of Prosthetic Dentistry, which is one of the top journals in its field. We published it in 2006. And we made this statement: this article reports on the first patient-fitted chromium cobalt removable partial denture framework produced by computer-assisted design, computer-assisted manufacture, and rapid prototype technologies. And we've made that statement, and the peer-reviewed journal printed it. So we were very proud of that. I'm going to give you a break now, because I've been talking for quite a long time. So by way of a break, I thought I'd show you some funny signs. And I don't actually mind if you talk amongst yourselves very quietly. Okay, feel suitably refreshed? Some lecturers would get you to stand up and wave your arms about at this stage. I won't put you through that. So, incidentally, in telling you about one of our firsts, I've missed out quite a lot of other stuff that we did, between 2006 and more recent years. We were doing things like testing the materials that were produced by these 3D printers and looking at things like biocompatibility and so on. But I'm concentrating on the sort of original stuff that we've done, and because that's what I personally get a kick out of. I suppose the technical term for what I've showed you so far is that you take something to a proof of concept stage. So our next proof of concept that we accomplished was in the field of orthodontics, that field about moving teeth around. It was fairly stimulating actually, because a PhD student sort of came to us and quite vaguely said, I'd like to do something in 3D printing and orthodontics, but that set us all thinking, and it was actually although it was vague, it was quite stimulating. And during this time, Dom had been, again, Dom and other colleagues had developed a technique of inserting wires into a build of something that was plastic. And, as soon as you say that to someone like myself, you just immediately think of orthodontics. Perhaps I could just talk about what myofunctional appliances are. There's something like this. It's quite a big block. It's a method of moving teeth around by using the pressures of the musculature that's around teeth, and teeth are actually moved. This is an appliance. Ortho people love to give posh names to all their appliances, and this was called an Andresen appliance. Now, there aren't many Andresen appliances made these days, but it was a simple appliance, so that's why we chose it to work on. I won't forget to switch to the PC this time. It's called a myofunctional appliance. No, don't be put off by the big word. But although we could build in resin and we could stop the build and insert wires, those wires had to be pre-bent and ready to be inserted. So how do you do it? Well, first of all, again, we have scanned dental models, and those are in grey there, and you can just about see the buff colour there, which is pretty well the shape of this plastic you can see here. Can you just see it? It's upside down, incidentally. The upper's, it's because the person there is working on it in 3 dimensions. And there's that appliance I just mentioned. It's a sort of buff colour there in the machine. And you have to, well, I didn't, but Dom did along with this PhD student, you have to build in channels into the resin build, which you can just see in red there. There are grey channels in the red areas. And these channels are for accepting pre-bent wires. How do you get the pre-bent wires? Well, you make little jigs, which you can see in blue there, and these are made from the same data as you've got in the resin block. So you know if you bend wire to fit those channels, you know it's going to fit the build. And so there we are, there are the jigs placed on the dental model. The wire was duly bent. You can just about see the holes in the, I wonder if this is on. Yeah, you can just about see the holes there, look. Ready for the wire to be inserted. Obviously you can't insert the wire in a block like that, so we stop it halfway and insert the wires. And we managed it. There's another build that was done digitally. Now actually, it was really quite difficult. And actually, it was a lot more difficult than doing it in the conventional way. So a few people wondered why we did it. Come to that, so did I really. But you will see an unintended consequence later on. So we'll come back to that. So what else did we do? Well, the technology of building was moving on, and in more recent years it was possible to build a hinge in a single build. And the way that was done is, you have little thin areas of wax between the parts, between the resin parts that you want to move. So I think we were the first to apply this. Well, I think we were the first because, again, we got it published and made one of those statements about being the first to do it again in a peer-reviewed journal. So although this technology was around, it hadn't been applied to anything dental. So these are devices which help people who've got difficulty with snoring. The hinges are just here and here and here, same on the other side. And the idea is if someone's got their mouth open, the lower jaw can be in a fairly centric position. But as soon as the lower jaw closes, those hinges force it forward, and the idea is that it keeps the airways open. So we built an anti-snoring device, and again, I think I keep saying I think we were the first to apply it to dentistry. Now, you can get these things digitally built before we did this, but the components came and the components needed to be assembled. So they're sort of clipped together. Well, the thing is, if you can clip something together, it can be unclipped in function. But there's no way this is going to unclip with stops like that and hinges like that. So again, we were pretty pleased with that. And there it is. So there's a sleep apnea device completed in a single build. And again, we got that published, American Journal of Orthodontics and Dentofacial Orthopedics. Need a deep breath to say that. And again, we made the statement, the article indicates that digital technologies can be applied to the fabrication of appliance types not previously considered to be possible. And there they are. They're in the top three, I think, journals in that field, and they work just behind that wall. They've got a photocopier and everything. No, they don't. So that takes us more or less up to the present. We've got a couple of current submissions, and the first one is, if we go back to the point where we were inserting wires, in between that point and now, I think we've seen what you might call the coming of age of intraoral digital scanning. Now, I know digital scanning of the oral tissues has been around for quite a long time, but it's been getting better, and it's actually, this is what it looks like. So you have a scanner, and it's taking many digital pictures of the oral cavity, and then it stitches them all together and builds up a 3D model of the patient's oral tissues. As you can see, it's a lot more comfortable than that impression I showed you earlier on. And why I say coming of age, it's now really pretty feasible to get an oral scan of the whole dental arch. Whereas, you could have, in principle, you could have done it a long time ago, but it's really quite uncomfortable. But now the scanners are smaller and neater, and it really is perfectly conceivable to get a scan of a whole arch, which is what you need if you're working in orthodontics. So if you, for example, scan somebody, this happens to be me. I was a sort of handy patient. You can see a thin blue line, so you could build up what you might call wire in that kind of area. And same with the buff colour clasp on the left there. You may have seen similar orthodontic items to that, but less bulky, just a plate. And those sort of clasps are used on those appliances. So he built a clasp, as you can see on the left there, in a buff colour. It was a bit more complicated than just outlining it. You had various planes to build and consider, which you can see on the right there. And all the wires in the colour of the model changes, but that's incidental really. It's the model on the top is the same as the model on the bottom. I know the colour's different. Don't be thrown by that. So the components that we built in a software environment can be seen in that buff colour. And then we sent them to Renishaw, and Renishaw printed them out for us. And that meant that you could build a whole appliance like this. That's it in the virtual environment. And we can pre-build the wires, and then when we start the resin build, we can stop it and insert the wires in the manner I described earlier. But what this means now with intraoral scanning is that you could, in principle, go straight from an intraoral scan, not bother with the dental model at all, and actually produce something that looks like an orthodontic appliance. And again, we managed to pull this off. We tried it in me. It wasn't perfect, but actually as a first stab at the problem, it certainly wasn't bad. And we felt that if we hadn't quite completely proved the concept, well, we jolly well nearly well had. And just sort of by the by along the way, had a bit of difficulty with that PhD student I mentioned during her viva. One of the external examiners was a bit worried about whether the dimensions in the virtual environment turned out to be the same as the dimensions that were actually printed. So we, never to let an opportunity go by, we tested it out, measured it, and that's something else that's currently under consideration and being reviewed. And that's basically where we are now. So just to recap, this network, this team, I've been really pleased to almost have fallen into the middle of, produced the first digitally built removable partial denture framework. We produced the first demonstration of inserting wires into a resin build, or the first dental application of it. The first use of built hinges, and the first demonstration about how to build a removable orthodontic device without the use of traditional impression or a dental cast. And that's where we are now. There are a few problems. There aren't actually very many, or well, I suppose there are none really, resins that can be built digitally that have long-term biocompatibility, but there are quite a few firms working towards this. In fact, one firm has done it, a firm that produces a resin called Peak, but it's probably not at the resolution that we need at the moment, but we're confident that we'll get there, or they'll get there, and then all this technology we've been using could be applied. Some of the appliances that I've been showing you and talking about and that we've produced digitally, then it must be said some of them are not used often at the moment. But think about what I was saying about unintended consequences. Imagine if you could scan a patient one end and then a machine builds an appliance such as the one we built. That might change the whole ball game, and it might, in ortho, there's a certain degree of fashion, and some appliances tend to be used a lot, and then ideas change, and then, there's a lot of toing and froing. But the fact that we've proved these concepts potentially are game changers. And, we have to wait and see what some of the unintended consequences are. So can we look forward to better dentistry? Well, if the discipline I mentioned, the crown and bridge discipline I mentioned earlier, is anything to go by, we can. The advantages to patients are that, as I said earlier, greater accuracy, potentially more comfort with scanning rather than impressions, probably better fit, cheaper, well, maybe over a 20-year period. Yes, let's hope. So just to recap, I hope you agree with me, there's been quite a lot of innovation, and I think myself and the team get quite a kick out of new knowledge. And there have been unintended consequences in this work that we've mentioned so far, and I personally fully expect there to be more. So sometimes it's worth just launching out and doing something just because you can, because you just never know at the time where it might lead, and often it does lead somewhere. And yes, what Thomas Kuhn said about different disciplines coming together, that's been really fruitful in this case. And then what about eccentricity, all that stuff about whether you need to be a little bit mad or a little bit lateral thinking, and all the stuff those people were talking about to Evan Davis. Well, personally, I don't think we're eccentric at all. Anyway, I'm very grateful to you all for coming, because as Jane Austen said, you're probably not as comfortable as you would have been at home. So, thank you very much.